Our next speaker is Mario Srouji, who was an intern at Apple this summer. Yes?
Under Ruslan Salahudinov.
Oh, under Ruslan.
Yeah.
Nice. The title of his talk is Deep Reinforcement Learning of Bipedal Walking with Structured Locomotor Nets.
Yeah, so hello everybody. It's great to be here today. So yeah, once again, I'm an intern under Ruslan here at Apple, also an undergrad at Carnegie Mellon, finishing my 4th year in computer engineering. And yeah, today I'm going to talk to you about our deep reinforcement learning of bipedal walking with structured locomotor nets. So I'd like to talk about 4 main things today. First, I'd like to motivate why did we decide to work on this problem, what are we trying to target, and sort of go over briefly what is the previous work that's been done, and then talk about our approach and some results. So walking in general, specifically bipedal walking, is a very challenging control problem. Oftentimes, it involves hand-tuned controllers, hand-tuned parameters that don't generalize very well to other robots. And a lot of times, it's difficult to sort of get a very natural movement, natural pattern of behavior. And this is an example of one of the simulations that we've been running. I'll talk about it more later, but so that's sort of the type of problem that we're trying to tackle. So previously, it's been shown that deep reinforcement learning is actually able to solve these types of problems fairly effectively. So briefly, what is reinforcement learning? It's a subset of machine learning where you have an interaction between an agent and an environment. And how that interaction works is your environment provides an observation at each time step to your agent. Your agent has to make a decision or take an action. And given that action, it receives a reward. And essentially, the goal of that agent is to maximize the accumulated reward over the episode. So reinforcement learning has been able to get sort of an approximation of walking in general through deep neural nets. But oftentimes, these nets are very hard to train end to end, and they can take a lot of time. So our goal was, can we create models that combine deep reinforcement learning and its power and ability to generalize, but also be able to put a sort of control structure to be able to train them very quickly, train them end to end, and also be able to form very natural walking movement. So this is our approach. Essentially what we did was we divided the problem into 3 main portions: a planning, nonlinear control, and linear control portion. And in each of these, you can replace them with very specific models depending on what you're trying to achieve. Specifically in this talk, I'll be focusing on walking. So how we started was we looked, okay, can we get a very simple model, linear model, to work pretty effectively on these types of problems? Can we train a linear model as a proof of concept and see, can this actually work? So that's what we did. We set up a linear model. So essentially what we're doing is we're learning a gain matrix K. And what we use it for is at each step when we get our observation, we multiply this matrix by the observation and produce an action. So a very simple linear control policy. But the way we're training this linear control policy is through an algorithm called evolutionary strategies. And briefly how it works is you have a vector of weights that you're trying to optimize. In this example, it's our gain matrix K. And essentially what you do is you create a population of different vectors and different vectors. And you do that by sampling random Gaussian noise into each one. Then running each vector on a full episode, getting a reward, and based on that reward, you do a weighted sum. And you reiterate this process. So we tested this on 3 different environments to see if this simple model can work and train effectively. So this is the first one. It's a lunar lander. So essentially the goal is to land this lander in between the flags by controlling the thrust and modulating thrust. On the right here, this was trained using a DDPG, actor-critic model. It took about 45 minutes to train. On the left, this is our very simple linear model. It was actually able to learn this behavior in around 40 seconds and using only 16 learned weights. So it was pretty quick. This is another example of 2 environments that we're running here. Oh, sorry. So here we're trying to do an unprotected left merge. And again, this linear model, while simple, was able to learn pretty quickly. And then more specifically to our walking environment, this is a bipedal walker from OpenAI. And in only 2.5 minutes, and using 96 weights, it was able to learn a rather crude walking behavior, but still be able to walk, which was pretty impressive for us. Because typically the type of models that were being used to train these simulations were fairly large neural networks that were taking hours to train. So after we saw this very simple model being able to effectively train, we said, okay, how can we bump up the complexity a little bit? So we revisited our structure and decided to add the nonlinear control portion. So now this is what the structure is going to look like for our next proof of concept. And specifically though, for walking, we said, what kind of nonlinear control can we impose on this model? So we tried to think, okay, what is a very natural way that maybe animals control rhythmic behavior? And that's where we came across central pattern generators. So essentially what this is they're biological networks in a lot of invertebrate and vertebrate animals. And they are able to produce rhythmic activity to control different motions. And they do so without sensory feedback. However, as we're going to see in a few slides, that sensory feedback is very important to shape the rhythmic behavior. So this is what we're going to be replacing in our nonlinear control. And how we're going to do the CPG is through emulation. So what we did was essentially we learned Fourier parameters. So we have n sinusoids, and for each one we're learning the amplitude, frequency, and phase. And then we sum them all up to get a rhythmic approximation of our function. This is a closer look at our model. So how this works is we have the evolutionary strategy algorithm directly training and optimizing our Fourier parameters. And then side by side, we're running our linear model from before for stability and combining them together to form our policy. So what we found when we revisited the same bipedal walker from OpenAI is we were actually able to beat the best performing algorithm in only 68 minutes and using only 288 parameters. So we were able to achieve a reward of 310 and produce very stable running behavior, which I'll show here. So here I have three videos here. The one on the far left, this is running our locomotor net. The one in the middle is the highest scoring algorithm on OpenAI, running DDPG, and then the one on the far right, this is the simple linear model from before. Ignore the tripping in the middle. So you can see the one on the far left, the type of running behavior is very different from the one in the middle that uses just deep reinforcement learning. It was actually very, very stable. This guy is sort of tiptoeing and bouncing on one foot. And this is looking at the output of one of the joints of the bipedal walker, looking at what is the central pattern generator outputting. So we can see that it's a very smooth, rhythmic type of pattern behavior, which is what we're trying to do. We're trying to target walking in a manner that we can produce these very natural movements. And as an aside, I mentioned before that central pattern generators do not need sensory feedback to produce their motion, but we found that it's very crucial to have that linear feedback portion to actually make the model very stable. Because when we ran the CPG model on its own, it wasn't able to effectively train. It was only able to achieve a reward of 27. So finally, we ran the model on much more complex environments. These are RoboSchool environments. They're Mujoko type environments. On the far left is an ant simulator. So you have a four-legged ant, and it's a pretty heavy animal in the simulator. And essentially, you're trying to get it to walk as smoothly and as quickly as possible. In the middle, you have a half cheetah, and on the right, you have a hopper. So interestingly, with the ant, the type of walking behavior it learned was very coordinated and very, very natural. Typically, with other deep reinforcement learning algorithms, the type of behavior you get is a hopping motion. So the ant will actually hop. But here you can see it actually coordinates its diagonal legs very well. And it was able to achieve a reward of around 1,800, which was able to beat the baseline in only around 70 minutes of training. Same for the half cheetah and the hopper on the right. So in terms of future work and what we want to do with this model, before we were using evolutionary strategies to train this model because we weren't actually using a neural network on the nonlinear side. We were directly optimizing the Fourier parameter weights. But for some future work, we want to incorporate policy gradient training. Additionally, the third portion in our structured model, we want to explore how can we use a planning module to further improve these walkers and also be able to have them avoid obstacles or manipulate themselves around obstacles. Additionally, we're currently also working on the NIPS Learning to Run challenge, which will be ending soon, but hopefully we can have exciting results on that as well. And since our structure involves a lot of priors from feedback control, we'd like to be able to see, can we incorporate analysis methods to really prove stability of these models? Yeah, and that's it. Thank you.
Thank you. We have time for questions.
Question over here.
Yeah, it seems very interesting work. Hold on a second. But it seems to me this is like a manifold learning, right? I mean, type of approach. In particular, you are like try to use multiple. I see that as multiple subspace. You try to learn multiple subspace, and of course, for a periodic motion, a harmonic function makes total sense. So that makes and of course, when you can do linear or orthogonal stuff, you definitely should factor that out first, right? I mean, is that sort of like how you approached it?
Yeah.
I mean, but then on top of that, you probably need to drive it by some kind of sparsity constraint to regularize it, right? So.
Sure. Yeah. So sorry.
Sparsity because you want a sparse model usually. So the way I see that you want to use sparse, like almost like a sparse representation to drive your subspace learning. I mean, it's just a comment. I don't really.
Yeah. Okay.
It's a raw
Yes.
idea. Yeah. I don't know whether. Yeah. Anyway. But
Yeah.
very interesting.
Yeah. Thank you.
Okay.
Yeah, one more question.
So, what constraints do you place on the model? You said, for instance, the spider walking was a better thing than the spider jumping, but are there constraints on energy or the maximum power that's required in the joints?
So in terms, did we modify the simulation at all, or produce?
No, like is the reward taking into account all of these things, or is the reward completely independent?
So the reward coming from the environment, I believe, gives you positive reward for moving forward. I think yes, it does. It does penalize for energy. The more energy you use, they weigh the ant pretty heavily, the body of the ant pretty heavily. So the more energy efficient you can be, and the farther you can go, the better. So yes.
Okay, let's thank Mario again.
Thanks. Thank you.